Hi, this is Professor Fernandez, and this is video 2 in lesson 25. So we're talking here about the linearization of transcendental functions. You see a couple of examples here on the screen from Calculus Simplified. So the first thing I want to mention is that because we are talking about linearization, and this is lesson 25, we've already done some work on this topic. So see the videos in lesson 13, videos 13.1 through 13.3. If you'd like a quick little review of linearization, I'll be using many of the fundamental formulas and just concepts from there in this video. Okay, so let's take a look at these two examples. What is here on the left? I'm going to zoom in a little bit. So suppose f of x is the natural exponential e to the x. First one says calculate the linear approximation of f at a equals 0, and then plot your result. Great, so quick little reminder, what is the linear approximation? It says f of x is approximately its value at a plus the derivative at a times x minus a. Remember, this part itself as a function of x is called the linearization of the function f of x, whereas this entire approximation is called the linear approximation. Okay, so that's enough of the quick little review there. And this is really what we're going to use for both of these examples and all of its subparts in this video. Great, so we need an a value to actually calculate this linear approximation. So that's given to us here, a equals 0. So I'm going to write over this approximation with a equals 0 and then follow what the math tells me to do. So I need two pieces of information, f of 0 and f prime of 0. We know f of x is e to the x, so f of 0, e to the 0, that's 1. And then we have to find the derivative. Remember that the derivative of e to the x, it's a very special function. Its derivative is itself, so that's nice. So that tells us that at x equals 0, e to the 0 is 1 again, so f prime of 0 is 1, f of 0 is 1. So I take those pieces of information and I put them in here. And I get f of 0, that's 1, plus f prime of 0, that's also 1, and then times x minus 0. So that's really just 1 plus x. So that is my linearization. Now, if I go back and put back in what f of x is, e to the x, this is my linear approximation. So what we're saying here is that for x near the a value that we just used, what we're saying here in this whole box now is that the function e to the x looks very, very much like the function 1 plus x when x is near 0. And so part B of this question, use your, plot the result, right? So I want to visualize that. So I've actually put in here, I'm going to zoom in, figure 4.6 from the book. You can see that this line in blue is the graph of y equals x plus 1, right? That's the linearization we just calculated. You can see that over here in black is the graph of y equals e to the x. And if I just zoom in a lot, 0 is over here. And if I look at a slice, try to make this a little thicker here. If I look at a slice, ooh, that's very thick. Maybe not. Let's try this one. Still no. So perhaps this one. All right, so that's pretty good. So if I look at a slice around x equals 0, right? I don't want to go too far in either direction. And I just look at this slice of the little ribbon of the graph. You can see that near x equals 0, the function and the graph of x plus 1, the linearization, look sort of the same. Certainly, if I were to make the slice even smaller and just look at this little segment, it's indistinguishable, really, at least to our eyes, at this level of magnification. So that's kind of the idea, and we talked again about that in the videos in lesson 13, the idea behind linearization. Okay, so we've done the work for part A, so let's move on to part B. Let me just erase the things that we don't need. So part B, use your approximation to estimate e to the 0.1 and then compare with the actual value. All right, so I'm going to leave our approximation there. Just zoom in to get rid of some of these things, okay? So what is the approximation for e to the 0.1? All right, so e to the 0.1, according to our approximation, is put in a 0.1 here for x, 1.1. You might be wondering, can I use this approximation for any x value? The answer is not quite right, so we want to make sure that we are near 0. and x equals 0.1, that qualifies as near 0. What about another value like 7, right? That's probably not near 0. So there's some fuzzy line between what is actually near 0 and what is not. And it's not quite clearly defined. But either way, right, you know that you're getting an approximation. And as both the graph and the theory tell you, the closer to 0 your x value is, the better your approximation will be. So all of that kind of gives you some guidance as to what range of x values you can use in this approximation, and it still make sense as an approximation. Okay, so what is e to the 0.1? That ends up being about 1.105 ... So the approximation we got here is 1.1, right? And there's a bunch of zeros here that are unseen. So that's pretty nice. So we got the first two decimal places correct, and the actual value starts differing in the third decimal place. That's pretty good accuracy for approximating something like e to the 0.1 transcendental function e to the x and the value there with a linear function, right? That's the whole point of linearization. So that's pretty cool. Okay, so let's take a look at the last example here. Show that sine x is approximately x for x near 0, and then similar thing for cosine x, approximately 1 for x near 0. Okay, here you are not given the a value explicitly like you are up here, but you are told basically the a value here for x near 0. So that's the a value, a equals 0 for both of these questions, this one and this one. So I'm going to go back again to my formula for the linear approximation, and I'm going to just write it out, because in both cases we are going to use a equals 0. F of 0 plus f prime of 0 times x, because a is 0. And then I again need the value and the derivative at 0 for each of these f of x functions. So over here we're going to do sine x, and then over here we're going to do cosine x. So f of 0, sine of 0 is 0. And then the derivative of sine we know is cosine x. So the derivative at 0 is 1. And then over here, f of 0, I'm now thinking of cosine x as f of x, is cosine of 0, that's 1. F prime of x, the derivative of cosine, is negative sine. And then f prime of 0 is minus sine of 0. We know sine of 0 is 0, so there we go. So these are the values I need. This one, and then this one, and then that one. Okay, so then taking these together, this tells me that sine x is approximately f of 0, which is 0, plus f prime of 0, which is 1, times x. Great. And then taking these two together tells me that cosine of x is approximately f of 0, which is 1, plus f prime of 0 times x. So you can see that this one simplifies to just x, and this one simplifies to just 1. And those are the two relations here we wanted to show. Okay, so, if I were to then graph this one, I didn't ask to do that, but just so that we have a visual of what's going on, we know, for example, that the graph of sine x looks kind of like this, so this is 1 and this is negative 1. And let's see, this is pi over 2 for x here, and this is pi. Okay, so this is y equals sine x. So you can see that if I were to zoom in here and I look at somewhere near x equals 0, here we go, and I plot the function y equals x, it would look like it this way, right? So again, near x equals 0, we have very good agreement between the values of y equals x and the values of sine x. So this gives us a way to approximate, I should say, up here. There we go. This gives us a way to approximate values, again, of a function which is kind of hard to wrap your head around, right? With values of a function, that's very easy to wrap your head around. You just, whatever the x value is, it's the same y value, y equals x. For cosine x, it's a little bit of a different picture, but it's kind of the graph of sine x, just shifted, right? So graph of cosine x looks like this, and this is y equals 1, negative 1, x equals 0, and then cosine of pi over 2 is 0, so that's pi over 2, and this is cosine of pi negative 1. And then so here for x near 0, right? If I'm here at x equals 0, this approximation tells me that if I plot y equals 1, then the values of cosine x are going to be close to the values of 1 as long as x is near 0. And you can see that that's true, right? In this little region over here, you can see that the y values of 1 are very close to the y values of cosine x. So once again, that illustrates that linearization. Okay, a couple of things just to say here to end this video. We've done two examples of linearization. In the first example, you were given the a value, so very explicitly. In the second example, you kind of had to discern this from the phrase for x near 0. But remember that when it comes to linearization, and specifically linear approximation, what you're using here is this form. And remember that this exact function, this is a linear function with slope f prime of a. This exact function is called the linearization. So make sure not to confuse those two. The whole thing, linear approximation, just the right-hand side, linearization.